In Physics 20, we introduced the idea of fields, the concept of fields. It was in the context of gravity, however. In general, a field is a line of influence that surrounds something. A gravitational field is a line of influence that surrounds an object with mass. We introduced the concept of gravitational fields simply because of this influence that's there no matter what. Gravitational field is essentially gravitational acceleration, right? We said the gravitational field that surrounds the Earth near the surface of the Earth is about 9.81 meters per second squared, or about 9.81 newtons per kilogram. If we have an object surrounding the Earth, or we have an object at this point above the surface of the Earth, it will experience the gravitational field of 9.81 meters per second squared and accelerate downward toward the Earth at that rate, 9.81 meters per second squared. But if I take this object away, the Earth, which has caused the gravity, doesn't disappear. In other words, gravity's still there, but it's not causing anything to accelerate. So let's talk about it in the context of fields as opposed to acceleration, because there's not always something that's accelerating. The influence is there, whether the effect is there or not. So a field is this imaginary line, really, that helps us to understand the idea that something's there even if there's nothing experiencing it. Gravity is there as long as the Earth is there to cause gravity. Well, we talk about electric fields in the same way. A field in general is a line of influence that surrounds something. An electric field is a line of influence that surrounds an electric charge. And it's very analogous in a lot of ways to a gravitational field, just like electric force was analogous to gravitational force. Similarities? Well, if we draw the gravitational field surrounding the Earth, we would call it a radial field. A radial field that radiates around the Earth. But it actually points toward the Earth because we define its direction as the way that an object with mass would move if placed in the field, right? Mass is always attracted toward the Earth. Mass is pulled towards the Earth. We have a similar shape when we have an electric charge that's the producer, as opposed to a mass that's the producer. We call it a radial field as well. The only difference here is that we have two kinds of producers, unlike for mass, where we only have one kind of mass, right? One kind of gravitational producer, because there's only one kind of mass. Two kinds of electric field producers. So how do we define the direction here now? Well, we arbitrarily, do you guys know what that means, arbitrarily? We arbitrarily define it in one way. What does it mean? Not by chance, but we just decide. Somebody at some point, not us, but somebody at some point decided this is the way it's going to be. Essentially, yes. Yeah. We arbitrarily define it as the way that a positive particle would move if placed in the field. If I put a positive particle right there, let's make it green here. Put a positive particle right there, which way would it go as a result of this positive producer? To the left or right? Would it go toward the producer or away from the producer? Away. It's repelled, right? That means that the field surrounding the positive producer goes this way. If I put that positive right here, though, which way would it go? It's attracted, right? It's attracted towards it. So the field in this case points towards it. Same shape as it was for the gravitational field. But in one case, it's the same direction. In the other case, it's the opposite direction. Both gravitational fields and electric fields are vector fields because they have a direction. No matter what that direction is, they have a direction. But there is such thing as a scalar field as well. Lines of influence that surround something, but that don't influence us in a particular direction. An example of a A scalar field might be a light field. Look up at the ceiling right now. You see the light bulb on the ceiling. That influences us, and it influences plants, and it influences all kinds of things, but not in a particular direction. Now, light will travel in a particular direction. If I flip off the lights over here, and then I turn them on again, the light will travel from the lights to your eyes. That's a direction. That's the velocity of the light there, though, not the field. The velocity of the light is a vector. The field, the influence of the light, is a scalar because it doesn't influence us in a particular direction. Same thing for a heat field. Okay, so we've got vector fields, we've got scalar fields. We focus almost entirely on the vector fields because we want to focus on gravity and the electric fields. Now, this comes down to the whole reason for introducing the concept of fields. Fields exist as long as we have a producer. We said the gravitational field surrounding the Earth is there no matter what. As long as the Earth is there, the field is there. Even when you're not there to experience the 9.81, the 9.81 is still there. It comes down to, some of you guys have probably heard about this or read about this or seen it on TV or some documentary at some point. Some of you guys may have no idea what I'm about to talk about. Einstein's theory of relativity, general relativity. Let's say we have a blanket. You're going to hold one corner, 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 and you're holding it tight. That blanket represents, for us, the fabric of space-time. We're going to put a little marble in one corner of that blanket. You guys are holding it perfectly level here, okay? We're going to put a little marble in one corner. What happens to that marble? Nothing, right? The marble doesn't go anywhere. Right? It just sits in that one corner of the blanket as long as you guys have it held tightly and as long as you guys have it held level. But now let's take a big heavy rock or brick and put it right in the middle of that blanket. Now what happens? We've just bent the fabric of space-time. There's a dent in the fabric of space-time. Now what happens when we put the marble in the corner over here by Oliver? Put the marble in the corner. Now what happens? It rolls toward the middle, right? Einstein said that's how gravity works. Space-time, X, Y, Z, and time, the four dimensions of space-time can be represented by that blanket. When we have something that's big and heavy and massive, it will dent the fabric of space-time, and that's why things are attracted to it. That's why the marble's attracted to the brick, because we've dented the fabric of space-time. The marble is going to follow the fabric, the bend in the fabric of space-time. Okay? If I drop something here near the surface of the Earth, then this thing will experience or follow the dent in the fabric of space-time. When something falls, it's sliding along, it's going along this slide down a hill along the fabric of space-time. Well, even if I take that marble away, the dent in the fabric of space-time is still there. So gravity is still there, right? I keep the brick in the middle of the blanket, the dent is still there. Gravity hasn't disappeared. We're using the field to explain that. As long as there's a producer, as long as there's the brick in the middle of that blanket, then there's going to be gravity. Okay, does that make sense? Kinda? There is a field as long as there's something causing it. However, there's not a force unless there's something to experience it. Think about the gravity thing again, Einstein's gravity thing again. There's a field as long as we have the brick in the middle of that blanket. There's only a force if we have the brick in the middle of the blanket and the marble over here by Oliver. You can't have a push or a pull if there's nothing to push or pull, if the marble's not there to push or pull. So you got a field, whether it's electric or gravitational, as long as there's a producer. You only have a force if there's the producer and something to experience that field. Now, we went through part of this definition already for the direction of the electric field. We said it was the way that a positive particle moved when placed in the field, if placed in the field. This was one producer, a positive producer. Remember, the field's there whether there's something to experience it or not. And the field has a direction that we have defined whether there's something there to experience it or not. We're not saying that we have a positive charge in that field right here. We're just saying if we did put it right there, which way would it go? Well, it would be repelled. It would go away from the producer. So although we don't necessarily have one there, if we did, it would go away from the producer. Hence, we define the direction of the field as being away from the producer. Similarly, if we had a negative producer, the positive particle, if it was there, would move towards it. Doesn't mean it has to be there, but if it was, it would move towards it. Well, that kind of goes to the second way that we define the direction of the electric field, away from the positive, as you can see in the first diagram, and toward the negative, as you can see in the second diagram. Here's a quick question for you. Let's put a negative right there. Which way is it going to go? Which way is that negative particle going to go? Towards or away from the positive producer? Brendan, you know the answer there, right? Which way does this negative go? Towards it or away from it? Good, towards it. Does that mean we have to change the field now pointing towards the positive producer? Who says yes? Who says no? Okay, a few people say no. How come? Why do we say no? Right. We arbitrarily define it as the way that a positive would move. Okay, a negative would move opposite to the field. It always does. But that's not really our concern because our definition is based on the positive. Which way would a positive move if there was a positive there? Which way would a negative move? Well, opposite, but who cares? Positive moves in the direction of the field. So although it would move toward the producer, we don't change the field there. The negative just moves opposite to the field. I'm going to draw a couple of diagrams here. 5, actually. 2 of them we've already drawn, though. The electric field surrounding a positive producer, we've drawn that. Okay. Field lines point away from it because that's the way that a positive would move if it was placed in the field. Okay, easy enough. What about a negative? We've drawn that one as well. We'll draw it again, though, just as a summary here. The way that a positive would move if placed in the field would be toward the negative. Let's draw another one now. What if we put the positive and the negative close enough together that they'll interact with each other, that they're going to influence each other? Let's draw a bunch of field lines surrounding the positive. There's an infinite number of them, by the way. We'll draw a bunch of them. Negative, again, there's an infinite number of them. We'll draw a bunch of them, not all of them. These field lines that leave the positive end up joining up with the field lines that go toward the negative. So it ends up looking something like this. We could draw more of them in there as well if we wanted to. The field lines leaving one join up with the field lines that go into the other. What's the next one? Well, let's put 2 positives in here now. These guys are close enough to interact with each other as well. They both have field lines going away from the producer. Something like this, right? There's an infinite number of them, but we're just drawing a few of them just for simplicity. These field lines don't join up with each other because these field lines are opposing each other. So when this field line from number 1 goes toward this field line from number 2, they actually end up doing this, pushing each other away. We could draw more of them as well if we wanted to. We don't have to, but. So the shape would look something like this, with a spot in the middle that has no field lines, meaning the field strength is 0. The density of the field lines represents how strong the field is. Okay, the field lines are pretty close together right in here. So it's a strong field. They're further apart out here, so it's a weaker field. Right here, there are no field lines. The field strength at that point is 0. Put a charge right here, positive charge right there. What's going to happen to it? Nothing. It's repelled by this guy. It's repelled by this guy. The net effect is 0. There is no field strength at that point. Yep. They always go away from the positive, out from the positive. Yep. Yep. You're assuming it's always acting on a little positive. Now, because that doesn't mean that there's always a little positive there. But remember, we define the direction of the field arbitrarily as the way that a little positive would move if it was there. So even if it's not there, we can pretend it's there. Which way would it go if it was there? Okay, away from the producer in that case. Brennan?
So that point in the center, is that kind of similar to the range point?
Yes, similar, yes. Yeah. Let's not go. Einstein's theory of relativity is bad enough, but yeah, we won't go there. But we could draw one more diagram here. I don't even need to draw it. What if I put 2 negatives here? What if I put 2 negatives here? What would it look like? What would the shape be? Yeah. What would the shape be, guys? You get an easy answer here. It'd be the exact same shape as we just drew, right? What would be the difference? Field lines would point in the opposite direction, right? 2 negatives. Field lines would look like this, same as they did in the last one, except the field lines would be pointing towards it instead of away from it. Good? Yep. Yes, that's a good question too. That's an instantaneous shape, but it's instantaneous before they repel each other. Let's assume that we're either looking at these at instant directionalities or those 2 charges are fixed. Because clearly, if they repel each other, they're going to move. And as they move, they're going to start looking further apart there, the weaker the field's going to be there. Okay, almost done here, guys. 3 equations you see up on the board right now should look familiar to you because you looked at them in Physics 20. The first one was my gravitational force equation. The second one was my gravitational field equation. If you have information about the producer. So if you talk about, let's say, the Earth as the producer, the pen in my hand that experiences the Earth's gravitational field. Well, if you have information about the Earth, that's the equation you use. If you have information about the pen, the experiencer, and you wanted to find the field strength, then this is the equation you'd use. You guys have used all 3 of these equations lots in Physics 20. Now, what are the analogous electricity equations? The first one we've already done. F is equal to K Q1 Q2 over R squared. Instead of dm1 m2 over R squared, we get K Q1 Q2 over R squared. What do you think the next one is? The electric field caused by a producer. I'm asking you to give me an equation that you've never seen before. And I'm asking you not to look at your data sheet. Invent it from your head. What's the equation that describes the electric field produced by something? Good. Excellent. Take Q over R squared. What's Q stand for, Aiden? K stands for the constant. What's Q stand for? The charge of the producing object, right? Yeah. So it's not just any charge. You may have an experiencer. I don't really care what that is right now because we're using the producer equation. You want the charge of the producer in coulombs. So if you go back to this equation for a second, the analogous gravity equation, this would be the mass of the Earth, not the mass of the pen, right? This is the charge of whatever's causing the field, not what's experiencing it. Finally, the last equation. Someone else is going to give you this one too. You guys are so smart, right? You can give me equations you've never seen before. You're inventing equations. And doesn't that make you like borderline genius? Yeah. What's this one going to be? The electric field experienced is what? F over Q. Good. Now this F would be the force that was experienced by something in newtons. And Q would be a charge, but this time it would be the charge of the experiencer, not the producer. So 3 new equations, but not really 3 new equations. 3 equations that work exactly the same way as you did in physics 20, except that you got a Q in there instead of an F. You got a K instead of otherwise the same. Let's try an example here. This is chapter 11 now. So if you haven't got that downloaded, download it tonight, please. 11.1 on 548, it says a sphere with a negative charge, circle that because I might make a mistake with that, of 2.1 times 10 to the negative 6 experiences this force when it's placed in the electric field produced by this source charge. They got a picture for me, but I don't need the picture. We can draw that. We can draw that ourselves. What's the magnitude of the field that charge produces? Let's draw a picture, okay? Like, this is a tricky question if we don't have a picture drawn in front of us. So let's do that now. Here's my negative charge. It experiences a force of 5.60 times 10 to the negative 2 newtons. That force is a repulsive force. It's away from, well, we'll call this charge over here that we don't really know what its value is. So that's we'll call this my source charge, produced by the source charge. We're looking for the field, the source charge right here produces at this point. What do you know more about? The thing that causes, tell me what it is that causes the field first of all. Is it number 1 or is it number 2 that causes the field here? 1 or 2? Number 1. Number 1 causes the field. What do you know more about? The thing that causes the field or the thing that experiences the field? Clearly, I think the thing that experiences the field, right? So let's use the experiencer equation, F over Q. Notice we're dropping the sign of the charge there. We never plug the sign of the charge into an equation. Let's see what we get there. 5.6 times 10 to the negative 2 divided by 2.1 times 10 to the negative 6. It's going to be 2.67 times 10 to the 4 Oh, what units should we use? Never gave you the units for electric field. Quick. Quicker you give me the units, the quicker we're done this. Newtons per coulomb, yeah. Hey, what do we know about this source? We're not asked anything else here, but let's just see what we know about it. Is there anything that we can determine about that source right now? What type of charge is it, positive or negative? Do we know that? We're not told that, are we? You can figure that out, though. Tell me, was it positive or negative charge, that source? Why do you say negative? Who said that? Stephen? How can we say negative? Good. If this guy experiences a repulsive force due to this guy, then this guy has to be a like charge. It has to be negative, right? What if the question said, well, wait a second, we found the field experienced by this one. That's not what we were looking for. We were looking for the field produced by this one, right? Isn't it the same thing? This guy experiences a field that's right here, that's caused by this guy right here. Okay, I got two sets of questions for you to work on. Practice problems on page 48, 548. In addition, there's one more example that kind of goes with this, but I think I'm going to skip that example. In addition, I want you to do the practice problems on page 549 as well.